Hello, everyone, and welcome to our third lecture for the SmartGrids course. Today, we're going to talk about IoT concepts and protocols. And in today's lecture, we're going to focus on physical layer and MAC layer protocols. Okay, so before we start, what is the meaning of IoT? IoT means the Internet of Things. And things was not, so the word things was not chosen for fun. It was chosen because there was no universal way of defining the devices that gets connected through this technology, and therefore they were labeled things. um, so if we look at the different devices that can be connected through IoT, we can start on the smallest level, the body area network, and this is the network that can go to the range of a human body. There we have included all the different wearables. So from your smartwatch to your dog's GPS chip to your different medical sensors for people, for example, with diabetes or people with uh, heart conditions. These kind of medical sensors, they measure a certain phenomena and they send signals to your phone in order to monitor a certain thing. And in the case of an emergency or in the case of something changing, like for example, your watch, when it detects an accident, so my Apple Watch can detect if I've had a severe fall, and it can automatically call uh, the emergency services and transmit my GPS location, right? So they can find me. So on this level, we have this body area network. On a slightly bigger level, we have the personal area network, and there we have the connected cars, a future technology that we think can be relevant to the idea of smart grids as well. So, for example, your car will automatically know which charging stations are working and which charging stations are out of order based on the state of the charger of the charging station, and it can actually direct you to the closest one in the neighborhood. And this is a way of having this smart behavior using IoT. On the same level, we have connected homes, right? So you have home automation systems, and this level falls within the personal area network. So this is on the level of a um, a room or an apartment, and this is where your home can manage itself. So, for example, you can have light sensors that measure the light intensity coming from outside and automatically turn on or off the lights based on this light intensity. Next, we have the local area network, which is the kind of level where most of the applications of smart grids lie. So there we have the monitoring systems that we talked about last lecture for power lines. We might have the smart metering systems that monitor the consumption at the user side. We can have traffic light systems that regulate automatically based um, on the flow of traffic. We can have as well the street light monitoring systems, and we will have an example about that later on in this lecture to show you kind of an actual implemented example of IoT networks. And this falls within the local area network. So this is one street, one neighborhood, maybe 1 kilometer range. And then we have the wide area network that can be a countrywide network, including the industrial internet, like factory automation, or we can have transportation. So these are trains on a country level communicating with different uh, bar switching on the grounds to direct the train in the correct direction. You can have oil and gas, so these offshore drilling bits need to be controlled somehow by offshore operations, and this requires kind of a wide area network, or healthcare services that monitor a country-wide um, or a countrywide distributed patients wearing different wearables. So they need to monitor these wearables at all times and dispatch a medical team in the case of an emergency, right? So you have different applications. All of these applications have different things that are being connected at the same time. And when you think about the applications using this technology of IoT, you don't really have a universal answer to how to design your algorithm, of how to design the communication between these things, of how to design the data management or the data analysis techniques. So each application in its own is a completely new uh, field. And that's why there are companies that are specializing in designing IoT um, solutions, but without defining exactly where your area of expertise is, you will never grow because each time a project comes, it can be in a completely different area. So you have to start from scratch, and therefore you don't really optimize your exact business business field. And this can be a very bad mistake at the beginning because you work at the beginning on, for example, sewage system monitoring, and then you work on the electricity grid, and then you work on wearables. First of all, you're working on different level of area networks. Then you're working on different technologies, different things that you need to monitor, and different amount of data that you need to transmit. And in the end, you don't really optimize one single solution for a specific service, right? And this is where people who are working in the IoT sector try to do. They try to focus their efforts on a single industrial sector and optimize this application for a specific purpose, right? But this is a different, kind of a different topic, and we can talk about that later. All right, so let's start focusing on what we want to talk about today, which is the physical layer standards and the MAC layer standards for IoT. Now, as we talked before last lecture about the different layers composing the internet design, we know that the physical layer and the MAC layer are the first two layers from the bottom, right? And they constitute the physical um, access to the radio band, so the transmission of the signal in the physical layer. And the MAC constitutes the MAC is a kind of a mix of the data link and the network layer, right? Because in IoT, this is similar to cellular networks. You don't really have the exact um, layer architecture as in the internet. That's what we talked about last time. This kind of different designing of the layers and how the gateways kind of do this translation as an interface in between. So this is what we have here. We have a MAC layer, which is a combination of data link and network layer. So this layer describes how the error correction at the packet level is, and on the networking level, you have how the distribution of the devices are. So if you have a mesh design or a star design or a ring design topology. So in the IoT domain, in the IoT ecosystem, there are different technologies using different standards. You have the Zigbee Alliance, which is one of the oldest IoT technologies out there. You have Bluetooth, which you have on your phones. You have Wi-Fi, which is a universal access. You have Z-Wave, LoRa, and narrowband IoT. Now, each one of these technologies have advantages and disadvantages. Each one of them has kind of a specific scenario that you would use it in. In this lecture, we will focus more on the Zigbee and the LoRa. So we will talk more in details about these two, and we will discuss different scenarios where you can choose Zigbee or LoRa. Right. So these technologies mainly describe the modes of operation in the physical layer and in the MAC layer. Now, when you go up, so when you go beyond these two layers, then you can use any other way of communication, any other communication protocol above these technologies. So you put LoRa or Zigbee or Wi-Fi in the bottom to describe how you transmit the signals, how you form the packets, and how you kind of build your network physically. And then on top of that, you write your application and your communication protocol any way you want. Right? You can use MQTT, HTTP, and we'll talk about that later when we go into the details of the upper layer, um, including the application layer. Good. So what are the different physical and MAC layer for wireless networks in general, right? So what is physical MAC wireless network standards? So one of the most known standard in telecommunication is the IEEE standard. So IEEE um, is a very powerful organization in the telecommunication, in the electrical engineering field in general, and they form these work groups that take it upon themselves to build these standards. The reason that we build these standards is because we want a universal guideline into how things work. Otherwise, each company can come up and say, we're going to do it this way, or we're going to do it that way. And when you have your Huawei phone, it might only work with Chinese companies, for example, and your Apple phone will only work with American companies. So you need to agree on a certain standard that all the different players in the ecosystem will kind of abide by. So the two most used standards in the telecommunication field is the IEEE 802.11, which is the standard for your wireless local area network. So this is your Wi-Fi at home or your local area network in general. And this mostly includes residential wireless devices, meaning your Wi-Fi routers. Most of these devices operate at 2.4 gigahertz, which is the normal mode of operation, and this follows the 802.11b or the 802.11g. And some high-end devices, more expensive ones, operate also at the 5 gigahertz following the 802.11a. And some even more expensive devices can operate at both frequencies. So if you ever went into your Wi-Fi kind of admin page, you can actually see if you have an expensive router, you can see which frequencies do you want to use, or even if you want to use both of them. Now, for 5 gigahertz channels, you actually get slightly faster speeds, but of course you're limited by the range of the connection. We're going to say why later on. Basically, it's the higher the frequency, the lower the range of communication is. And also, there is another reason that you would want to work at the 5 gigahertz um, in case you have a low range of communication. In case that's okay with you, you might want to work there because the 2.4 gigahertz is actually an open band where a lot of technologies work. And we're going to show that in the next slide. The second important standard that we want to talk about is the IEEE 802.15. And this standard constitutes a set of rules for different technologies to work. Now, in general, the .15 is a standard for low-rate wireless personal area networks. And these wireless personal area networks, or this standard, has 7 different work groups. Now, each group works on a specific technology or a problem, and they come up with some guidelines for everybody to use. Now, .1 we'll talk about Bluetooth. Dot 2, we'll talk about the coexistence of different technologies operating at the same at this 2.4 gigahertz. The dot 3 is the high rate wireless personal area network. The dot 4 is the low rate wireless personal area network, and this is where we're gonna get into more details. Now, the dot 5 um, looks more into how can you connect a network in a mesh topology and actually enable these devices to route the information throughout the network. The dot 6 talks about the wearables body area network, and dot 7 talks about visible light communications. Now, all of these networks have one thing in common, which is they are all low power networks, right? So they all rely more or less on battery operated devices. So let's get into more details of the 15.4 or the low rate wireless personal area network. Now, the 15.4 can operate at the 868 megahertz, that's in Europe, or the 802 megahertz in the US. And it can also operate at the 2.4 gigahertz, which is mostly unlicensed spectrum, or as also commonly known as the ISM band, which stands for Industrial, Scientific, and Medical Band. That means that anybody working at the industry, science, or medicine, they can use these bands for transmitting information. It's completely unlicensed, and you're free to use that. Otherwise, if you transmit other frequencies, you might, for example, um, interfere with satellite communications or with military communications, and then you can get in trouble. Now, this specific standard is kind of the basic stone for a lot of technologies, including Zigbee, wireless HART, and the 6LoW WPAN, which operates over low power wireless personal area networks. We're going to focus more on Zigbee in the next slide. And if you guys want to look kind of more closely at the operations of the IEEE or how a standard looks like, I will upload the IEEE 802.15.4 to the lecture folder on Opal, so you guys can have a look at that. Okay, another thing about the 15.4 channels is that operating at the 2.4 gigahertz, you actually have severe interference with Wi-Fi channels. So in the bottom curve, we have a kind of an illustration of different Wi-Fi channels and different Zigbee channels. Now, these kind of mountain-shaped like channels are the Zigbee channels, and these wider channels are the Wi-Fi channels. And as this means actually the height of the channel is how much power is being received at a certain frequency. So you can find here, for example, channel 11 for Zigbee is operating at 2.405 gigahertz, or channel, I don't know, 25 is at 2.475 gigahertz. While channels of Wi-Fi are wider in bandwidth, so you can actually transmit more data, but they are lower in power. So a question that I want to ask for you guys here, and you can think about it, is if you have a Wi-Fi router at home and you don't have the option to operate at 5 gigahertz, so you can only operate at 2.4 gigahertz. And at the same time, you want to set up a Zigbee network inside your home to, for example, control your lights. How would you go about into choosing the channels that uh, that you can use for your operation, right? So think about that question, and in the next live session that we have, you guys can give me the answer, or we can discuss that further. Good. So in this slide, so now we're going to go into more details about Zigbee. And actually, Zigbee is an alliance that was formed by a nonprofit organization that was established in 2002. Now, Zigbee is mainly a protocol that can run on off-the-shelf battery-operated sensor kits that are pretty cheap. So you can actually buy a couple of them and kind of tinkle with them a little bit and connect them in different ways and kind of like test it yourself. Now, the Zigbee follows the IEEE 802.15.4 standard, which means that it operates at the previously discussed frequencies. So it operates at 800 megahertz or 2.4 gigahertz. The communication ranges for Zigbee are actually up to 20 meters when you don't have line of sight, means that you have kind of obstructions in the way of your signals, and it can go up to 100 meter if you have a line of sight connection. The transmit power of these devices are typically from 0 to 3 dBm. The receiver sensitivity, which means that this is the minimum acceptable received signal strength for a successful recovery of the data, are negative 90 to negative 100 dBm, which gives us a link budget of 90 to 103 dB. Now, the definition of a link budget is the difference between the transmitted power and the minimum allowed received signal strength. So basically, you take the maximum transmit power. So the possible transmit powers here are from zero to 3 dBm, or actually the maximum allowed transmit power are from 0 to 3 dBm, depending on the device that you have. Some more expensive devices can transmit a higher power. And then you have the receiver sensitivity from negative 90 to negative 100 dBm. So some more sophisticated receivers can receive at lower powers. So therefore, the difference between these two gives you a link budget between 90 and 103 dB, depending on the sophistication, on how expensive is the device that you are operating on. Now, this is regarding the physical layer, right? And now when we go onto the MAC layer, we can see here on the right side kind of a depiction of a Zigbee network. And we can see that the Zigbee devices, the end devices, so these are the sensor nodes, are depicted in green. So here they are distributed. Each node is measuring a certain thing. So here, for example, this one is measuring the temperature. This one is measuring battery level, the brightness of the screen, the video recording, and for example, the doors, right? And then you have a router that kind of connects these end devices to the coordinator, because as we said, the range of communication of these devices is not very far, so the data cannot travel from the end devices all the way to the coordinator at sometimes. So you need to have a switch in the middle, or a router or a repeater, in order to kind of make the signal travel further. And then you have the coordinator that kind of gathers the information and also synchronizes all the nodes in the network, and sometimes distributes updates in firmware for these different end devices. So as you can see, in a way, this can be either arranged in a star topology. If you eliminate all the routers and kind of connect all the end devices to the coordinator, this means that you would have a star topology. Or if you prefer to have longer ranges, then you can have a mesh network, which means that the signal will travel through multiple nodes in order to reach the coordinator. Now, this coordinator is connected to the outside network, that can be a home network or a factory network or even the internet directly using cellular networks or anything. And then it connects to a database where your application is running and your data can be stored. Good. So, as we said, a coordinator node is responsible for managing and routing the information, also the synchronization in the network. The mesh topologies are preferred usually with Zigbee because it reduces, due to the reduced range of communication of Zigbee, and you can actually uh, construct multiple hop networks. However, you would have a hard to calculate latency because depending on the optimal route, the information might not take the shortest path, but it can actually take a longer path. So you don't always know which route the information will take, depending on the congestion in the network. So you might have unpredictable latencies. After that, let's go back a little bit into the physical layer of Zigbee and talk about modulation and data rates. Now, the modulation of Zigbee is offset QPSK. I know that you guys might not be familiar with modulation techniques in digital communication. However, I will try to explain it as best as I can. You're not required to know it by heart because this is not the purpose of the lecture. However, it would be nice if you guys understand that. If you don't ask me questions, you can also look it up online. There are multiple videos that shows you in an interactive way how modulation schemes look like. Okay, so offset QPSK looks kind of similar to the modulation in general in Zigbee looks similar to the diagram that we have here. So first of all, you have 4 bits. So these can be ones or zeros. So this is in binary, right? Now these 4 bits are mapped. So bits 4 to symbol mapping. So these 4 bits are mapped to a symbol. So this certain symbol is is these 4 bits. So this describes the baseband signal. Now, this symbol is multiplied by a chip sequence that is in the standard in the IEEE 15.4 that you guys will have in the OPAL folder. So you can actually look at different chip sequences. So these are 32 bits. Now, the reason why it's called chip sequence is because it spreads the baseband signal from 4 bits into 4 multiplied by 32 bits. So what happens is that you have a certain, let's call it spreading sequence, right? So this chip sequence, 32 bits. Now these are multiplied by these 4 bits, either zeros or ones. So if it's a 0, then all the bits are flipped. So the zeros in the chip sequence become ones and the ones become zeros. And if the original bit in the symbol is 1, then the chip sequence stays the same. After you multiply each bit by a chip sequence, you concatenate the resulting 32 bits. So you will have 32, 32, 32, and then 32. And then you take the odd bits and you put them on the in phase part of the signal, and you take the even bits and you put them on the quadrature part of the signal. Now this is kind of like a rough explanation of how the modulation happens. You can see here the in phase have these sinusoidal-like um, peaks and valleys, right? And the quadrature has here. So you start at the odd, and then you have here the even bits. Also look like a sinusoidal kind of like peak and valley. And here you can see Um, the ones are the 90 phase shift, and the zeros are negative 90 phase shifts. I don't want to go into details of the modulation technique, but this is for your own, for your own information. Good. So sorry. The data rates of Zigbee are different depending on the frequency that you're using. So as we said, the higher the frequency, the higher the data rates you can achieve. However, you get even lower ranges. And we're going to show that in an example how the frequency kind of defines the range of communication. Right. So we're going to take a break here, and then we will continue with Laura.